All right, welcome to day 23, our final day of new material in this unit. Homework, you got page 15, 16. Remember to do that on a separate sheet of paper. So we want to find our Maclaurin series and its interval convergence. Got to have at least 3 terms in the general term. So I showed here initially how you could do that the long way, how you could take your at least 3 derivatives, sub in 0 because it's Maclaurin, and build it out. But we would hope that you would be able to start right here by recognizing that's our geometric sum and we're just multiplying by x each time. So you would need to have at least the 1 plus x squared and then your summation. From there, we got to do our interval of convergence, limit as n approaches infinity of next term divided by current term. That'll just be x. So we get -1 to 1 initially. We'll check -1 by subbing it into there. That's just going to be -1, -1, 1, -1, so the terms don't approach 0, so diverges by the nth term test. Same idea when we sub in 1, so our interval does not include the -1 and the 1. Now these next couple questions kind of build off of each other. So we want 1 over 1 plus x squared. We can take what we did in the previous question and just sub -x squared in. So in this line here, you would need the first 3 terms and then the summation you would need. So our interval of convergence, do next term divided by current term. You again get x back, so you get -1 to 1. You're going to be subbing those -1 and 1s in our summation when we check the endpoints. So we'll have -1 to 3n, that neatens up to. Well, when you put in 0, you're just going to get 1 back. When you put in 1, you're going to get -1 back, and it's going to alternate. Those don't approach 0, so it diverges by nth term test. And same idea for the other one, so our interval does not include the -1 or the 1. So for arctan, you could either build off of the last one, because 1 over 1 plus x squared's antiderivative is arctan, or that's one that would be helpful to have memorized. So if you have it memorized, you need to have at least those first 3 terms and then the summation. Okay, and we have there how you would build it out from that previous answer if need be, if you didn't have it memorized. I would suggest to have that one memorized for the test. It'll be really helpful. So now do your next term divided by current term. We have 2 extra x's on top, so you have an x squared. Have our n's in that fraction there. When n goes to infinity, it'll be ratio of leading coefficients, which is 1. So we'll just have x squared. X squared stays less than 1 when x is between -1 and 1. We're going to have to check our endpoints in here. So when we sub the -1 in, we'll get 3n plus 1 in the exponent when we neaten it up. When you put in 0, you'll have to an odd, so that'll be negative. When you put in 1, you'll have to the 4th for the -1, so that'll be an even. So it's going to alternate signs. Our terms are going to the 0 because the denominator is going to get bigger, and each successive term is smaller than the one before it. So we can say converges by the alternating series test. And we're able to do pretty much the same thing for x equals 1. So in our interval, both -1 and 1 were included. In 4, we want to do arctan of x squared. So you could take your previous answer from 3, fill in x squared. You need at least 3 of those terms, and then the summation. So do next term divided by current term. You had 4 extra x's on top this time, and then similar idea for the n's. Those go to 0. We have x to the 4th, which stays less than 1 when x is between -1 and 1. You're going to be subbing into here your endpoints. Well, if you neaten up that numerator, you'll have -1 to the 5n plus 2. But when you have 5n plus 2, when you sub in 0, you get back when you sub in 0, you get back 1. But when you sub in 1, you're getting to the 7th, so that's odd. So it's going to, you can either leave it as -1 to the 5n plus 2, or it's just going to behave like -1 to the n. That's what I wrote there. So in other words, we need to know that it alternates. Both of our conditions are met for alternating series tests, so that's going to converge. Now when you sub in 1, that 1 to the 4n plus 2, that's just going to be 1, so we just have -1 to the n. So again, that's going to meet the conditions for alternating series tests, so that'll converge. So we are including both the -1 and 1 in our interval of convergence. Moving on to 5, we're going to find a series for cos squared x, 3 terms in the general term again, and we're going to use the idea that cos 2x is equal to 2 cos squared x minus 1. So we're going to build cos 2x, and then we'll rearrange to get the cos squared by itself. So start with what we know cos is. You've got our terms, you got the general term. Sub in the 2x to both our terms and the general term. And then getting it the cos squared x by itself, you're going to have to add 1 and then multiply by a half. So adding 1 and then multiplying by a half is now going to give us 2 halves out front. And then all our exponents of 2 have been, 2 have been dropped down. Now it's 2 to the first, 2 to the third, and so on. So if you neaten that up, our pattern really starts here, because that was our cos x summation. So you can do 1/2 out front and then do your summation. And I always just like to sub in a couple of the bottom values of n just to make sure it works out. So you needed at least the first 3 terms and then the general term. Similar idea, we're going to do 2x cubed sine x cos x. Well, sine 2x is 2 sine x cos x, and then we would have to multiply by x cubed. So start with our sine x terms, and then the general term. Sub in 2x. That's now the same as 2 sine x cos x, and then multiply by an x cubed. So the powers in our x's gets multiplied by 3. For that bottom line, just make sure you have at least 3 of the terms. So if you had that and then that, you would be all set. All right, in 7, it just said we had to find a series. It didn't say we had to find at least 3 terms. So I did more work than I had to here. Really, you could have just done the work that's under that line. So we know our derivative is what they give to us, and then we should have times x to the n over n factorial, because it's Maclaurin. So then from there, do your next term divided by your current term. We get some stuff to wipe out, and then I want to talk about this here. As n goes to infinity, the exponential parts are what are going to control the value of that. So you can basically ignore the n plus 1 squared and the n squared, because when n gets huge, they will not affect our value like the exponential will. So we can think of it as 3 to the n plus 1 over 3 to the n, and that's why it simplifies to just a 3 in that spot. Well, now as n goes to infinity, you still have that n on the bottom from the n plus 1, so that's going to 0. So 0 is always less than 1, so this is going to converge for all values of x, so our interval of convergence is -infinity to infinity. So for this one, we've got that our value at -1 is 8. Then our derivative, first derivative is 0, so we have 0 times x plus 1, which will end up going away. And then our derivatives after 2 are given by the expression there. So we have, these are our derivatives after 2, You have your center raised to the n, and then over our n factorial. Notice this summation is starting at n equals 2. And then you could neaten it up to not include the 0 times x plus 1 if you want. So our interval of convergence, we're just doing the summation part. We end up getting a similar scenario to the last one. When n goes to infinity, only the exponential parts are going to matter. So you're going to have an extra 2 on the bottom, so we have the half there. So multiply the 2's over, and then subtract the 1. So our initial interval of convergence is -3 to 1. We're subbing those in to here. So we'll have a -2 to the n. In the denominator, the 2 to the n is going to control the value. The n squared is not going to be that significant when n gets enormous. So, because of that, our values are not going to go to 0 because they'll balance off with that -2 to the n on top. And if you just do out a couple terms, you can kind of see that. So notice we're at a half, a little less than a half, back to a half, but now we're more than a half. So we are growing eventually. We're not heading towards 0, so this would diverge by the nth term test. And it's a similar idea when you end up subbing the 2 in. So you just don't include the -3 and the 1 in your interval. Now, question B is a popular one on the AP exam. We want to know if -1 is a relative or local min or local max or neither, and we got to tell why. Well, the fact that we have the first derivative was 0 tells us it's a critical number at -1. And then think of your concavity. If you're concave down and the derivative 0, it would be a local min. Or sorry, local max over here. If you're concave up and a derivative of 0, then you're, yeah, I was right the first time, local min. If you're concave down, then it's a local max. So if we can figure out our concavity, if it's concave up at that spot where the slope is 0, we'll have a local min. If it's concave down, we'll have a local max. Well, the second derivative tells us that. So just take our expression for the derivative and fill in 2 to see what you get back. Well, when you fill in 2, we get that second derivative is a fourth. So that means we are concave up. So we would say by the second derivative test, since our first derivative at -1 was 0, and the second derivative at -1 was positive, we must have a local min. And that's a really popular question on the AP exam. Moving on to 9, we can start with our arctan. Now I have the general terms there, and I built it out, but hopefully you would be able to start down here. And we don't need the general in this case with the limits, so in reality, if you just have this side, we're in good shape. So have those, divide by x to get these, and now limit as x goes to 0, all the terms except for the 1 go away, so you get 1. All right, start with your cosec. Sub in a 3x. We need the general terms because we want to write it as an infinite series eventually. Subtract your 1 and divide by x. Then we want to do our antiderivative. So do your antiderivative of everything. We initially have the c there, but because we're going to sub in 1 and 0, we don't need to worry about the c. So here's where we're going to sub in. The 0 is going to wipe everything out, and those natural logs wiped each other out too. I could have gotten rid of those here as well. Sub in your 1 for x, and that's what we get for our value of our integral with everything subbed in. Well, then they wanted us to use the first 3 terms. So sub in your n equals 1, n equals 2, and n equals 3, and fill in 1 for x. And this gives us the first 3 terms, so it's a approximation by our partial sum. We want to know what our error is. It's an alternating series, so we can use alternating series error bound. So we have to do the absolute value of the next term, so just ignore the -1 to the n. So for 1, or for x, you're putting in 1, and we're now to the 8th powers for all of them, and the 8th factorials, so you either get that fraction or that decimal. In 11, that's really e to the negative x, so start with your e to the x. Fill in a negative x. Do your antiderivative. We don't necessarily need the c here because we're going to be doing our subbing in. Make sure you use the general term of your antiderivative. When you sub in 1, we'll get what's in black there, minus what you sub in 0. It's just going to all go away. Then they wanted us, just like the last one, to use the first 3 terms, so we get 2/3. And then alternating series, error bound, so use your 4th, sub in 1, and we get that our error is 1/24. All right, so our lesson for today is pretty short. So first, a kind of joker riddle. Why do Maclaurin series fit the original function so well? Because they are tailor-made. So what we have here is a compilation of all of our common ones that we've seen. You got to have those first 4 memorized to have any shot of doing well at the test. The next one that I would say would be good to memorize is arctan as well, just because arctan, it's a bit of a pain to derive from there. These ones here are not as bad to get from 1 over 1 minus x, but I would say maybe memorize arctan as well, because that's a bit more of a pain, because you've got to do it from an antiderivative for the 1 over 1 plus x squared. So what I do is I put these on a note card at the start of this unit each year. And what I do is I just keep that note card in my pocket and I quiz myself when I have downtime. So if I'm eating breakfast or something, I'll quiz myself, check it. If I'm eating lunch, if I got 5 minutes, I'll quiz myself just to make sure I have them rememorized. So a good idea would maybe be to put those on a note card and 6, 7 times a day when you got 5 minutes, see if you can quiz yourself and if you've got each of those memorized. Having those memorized will make your life a lot easier for the test. So what we want to do is try and take these series and write it as a function now. So we're going to go the opposite direction. In this first one, we want to notice that we're starting with 1 and we're multiplying by 3x each time. Well, those are all being added up, so this is just a geometric sum. So we have our first term over 1 minus what we're multiplying by, so 1 minus 3x. And that's it. For the next one, we want to notice that we have odd numbers in the denominator, but they are not factorials. And notice we have alternating signs. So if we look at our list of common ones, odds in the denominator, no factorials, alternating signs, that's arctan. Well, then think about what got subbed in for x. All the x's were replaced with 7x. So this is just f of x equals arctan of 7x. So these problems basically come down to recognition of our basic ones and then what has been altered or subbed in for them. Going down to the bottom, you want to recognize that you have odd factorials and your alternating signs. So we would probably think sine there, but notice the powers don't match the factorials. The powers are all 1 less. So this would be a sine x, but because the powers are all 1 less, we must have divided by x. In the next one, we've got even factorials. We're alternating signs. And notice that our powers are matching up. So initially, this was x squared, x to the 4th, x to the 6th. So we got to think about what got subbed in to give us each of those. Well, in our cos x, that would be if we just replaced x with 5x. Because 5x all squared gives us 25x squared. 5x all to the 4th gives us 625x to the 4th, and so on. So that's what we would do if they wanted us to write what the function would be that would match this series. Now, if we wanted to find the exact value of the series, we've basically got those functions, but with a specific value filled in. So in this case, we want to recognize we're multiplying by a third each time. So this is geometric. We're starting with 6. We've got 1 minus 1/3. So this will give us 6 over 2/3. That's really 6 times 3/2. So this should just add to 9. The next one, we've got odd factorials with alternating signs. So we want to think sine. In place of x has been placed a pi. Sine of pi is just 0. And our last one for today, we've got all the numbers. They're not factorials though. And you've got alternating signs. The powers on top match the numbers on the bottom. So we want to look for one that has alternating signs, all the numbers on the bottom, and the matching powers. So that's here with natural log of 1 plus x. So we've just got to think about what has been subbed in for x. So we're going to have natural log of 1 plus something. And notice the thing that was subbed in for x was e squared minus 1. Combining like terms is natural log of e squared, and natural log of e squared is just 2, because that's really 2 times natural log of e, and natural log of e is just 1. That's it for today's video. Have a great rest of your day.